These are your Chapter 8 takeaways on chemical bonding. I'll try to make this as short as possible. So at the beginning of Chapter 8, we started talking about, it was the only section we talked about ionic bonds, of course, which exist between, a cation and an anion. They involve the transfer of an electron. And ionic bonds are governed by something called lattice energy, which is the energy required to completely separate 1 mole of an ionic solid into its ions in the gas form. So an example would be like this. Okay. Excuse me. And it would be the energy value to do that. And this is where we learned that it depends on 2 things. The ionic charges. So is it +1, is it +2? And the distance between them, or the size of the atom. So we made kind of a bold statement somewhere on our note paper that lattice energy increases as the charges increase. And that's because if you think about it, a +1 -1 compound is not held together as tightly as a +3 -3. And so that +3 -3 combination is going to take much more energy to separate. And then that lattice energy increases as the distance between the charges decreases. And this goes back to that Coulomb's law, which of course we know we'll never have to solve, but it's worth talking about and discussing. Okay, that these things depend on the ionic charges and the distance between them. Okay, so then of course we move into Lewis structures, which are 2-dimensional pictures, which we know that's a big deal now that we've talked about geometries. Okay, they're 2-dimensional pictures that show the sharing of electrons in covalent compounds. Okay, and I'm not going to go through the rules because I know you know how to draw a Lewis structure, but we know that there are lots of things that come under the kind of the umbrella of Lewis structures. One of them being resonance, which is where electrons can resonate back and forth, and that's because they're not stationary. So something like, I think the example we used in class was O3. And so while this is a valid, I'm missing a lone pair, sorry. Well, this is a valid Lewis structure for O3, so is this. Because those electrons are not attached, so to speak, and they can move around. And so this is where we talked about, that we know that the bond lengths can be different if it's a single, double, or a triple. But then in this case, the bond lengths are all the same. And, scientists kind of said, how can that be? And we realized that the true picture is an average of all the structures. And we talked about, so what is then this bond? And what is this bond? Is this really a single and really a double? And it's not. So the way you find that is by taking the number of bonds and divide it by the places that they can be. So in this case, we have 1, 2, 3 bonds divided by the fact that they could be here or here, so divided by 2. So in ozone, The bond length, or the bond is actually a bond and a half. So it's not a single, it's not a double, it's a bond and a half. I know that's hard to picture. It's also very hard to draw, which is why we draw it as a resonance picture. Okay, I'm looking through my notes because I don't want to miss anything. All right, so then we learned formal charge, which basically is basically it's a way to pick the best Lewis structure. Way to pick best Lewis structure. We know sometimes we can draw numerous Lewis structures, but there's always a better one, or it's not a better one, there's always a best structure, and so that's calculated with formal charge. And we calculate formal charge by taking the valence electrons, subtracting the assigned electrons. So let me give you an example. In water, right? So we would come, and I'll just change my color. Hydrogen has 1 valence electron, and in this bond, it's assigned that 1 valence electron. So 1 minus 1 is 0. Same thing for this one. And then oxygen has 6 valence electrons, and in this case, it has 1, 2, 3, 4, 5, and 6. So formal charge on oxygen is 0 in this case. So that's how you calculate formal charge. And then the way we pick between Lewis structures, so the best structure, first and foremost, has formal charges closest to 0. So like that's why water, that's why water structure is what it is, because it has all 0 formal charges. But then if that doesn't allow you to pick the best structure, then the best structure has a negative formal charge on the most electronegative atom. And remember, electronegativity, which we'll talk about in a minute, with polarity, increases up and over. All right, then we learn that while it's important to know that the octet rule is followed a lot of the time, it's not always followed. And so there are a few exceptions, and you should be aware of these. The one that's probably least, worth being aware of is this first one of having an odd number of electrons. But you should know that if you have an odd number of electrons, you'll never satisfy the octet rule. The second one occurs when we have a structure that is a okay structure with less than 8. And that primarily happens with B and BE. A great example is BF3, whose structure looks like this. And we very quickly see that boron does not have an octet, it only has 6, and that's okay, that's its structure. And then the expanded octet, which would be your octet rule, violators by going over 8, and that primarily happens with sulfur and phosphorus. So just things to be aware of. A couple almost trend type things in talking about when we have a single bond, a double bond, and a triple bond. So we know that a triple bond is the strongest. Okay, so I'm going to just label that arrow as strength. So a triple is stronger than a double, and a double is stronger than a single. We also know that the energy needed to break increases as we move from single to double to triple, and that is actually referred to as bond dissociation energy. And then the third one is opposite, and that is bond length. And so a triple bond is the shortest bond, and a single bond is the longest, and we're referring to the distance between the atoms. So, if you had a carbon single bond versus a carbon triple bond, I'm exaggerating it here, but the carbons will be closer in the triple bond. Okay, and then we learned about bond polarity, which is the degree to which atoms share electrons. So a nonpolar bond occurs when we have an equal sharing of electrons, and thus equal or almost equal electronegativity values. There's 2 cases you should always be aware of. Those are diatomics. and carbon-hydrogen bonds are considered to be nonpolar because they share the electrons almost equally. Almost everything else is a polar bond, where we have an unequal sharing of electrons. It's caused by differences in electronegativities. And then if we have a polar bond, our molecules will have partial charges. So that's like, HCl. Okay, if we think about the bonding between hydrogen and chlorine, chlorine is more electronegative. It wants the electrons more of the time. So there's two ways we can denote the partial charges that occur. The first way is giving the chlorine a partial negative and the hydrogen a partial positive. That's one way. And the second way is the arrow, and it points along parallel to the bond toward the more electronegative atom. We've also now learned that molecules will arrange themselves according to partial charges. So if I was going to bring in another HCl, it would probably do something like this, because that partial negative and partial positive are very much attracted to one another. And so those are your partial charges that occur in polar molecules. Okay, and then the very last thing, which I'm not even going to do an example because I know you have examples in your other notes and your other takeaway, would be that we can calculate delta H by taking the energy needed to break all the bonds and subtracting it from the energy needed to form all of the bonds. And so that is the fourth way to find delta H.